Hello, welcome to a new video. Today we're in this problem called binary tree right side view 199 medium code on medium problem on LeetCode. I did solve this, but using that first search, which I thought was pretty cool because I solved it without searching it up. But LeetCode, um, I'm doing the blind 75. But I took a stop here because I just wanted to learn. But then I went on LeetCode, his whatever like problem tracking guide, whatever, and I did all the binary search tree problems, and then I did binary tree right side view. I did it using depth first search, but now I'm kind of very comfortable with binary tree, so I'm just gonna come back to LeetCode 75, and then continue on with it. And I left off here. Well, I completed this, so I left off here technically. So yeah, so we're back here at binary tree. We're on the last way to binary tree. They're on a graph, and then I'm probably going to do graph on LeetCode. And then once I'm done with graph on LeetCode, I come back here and try to solve these, and then heap and so on. But anyways, I'm not sure why binary search is like right here. It should be like back here. But anyways, so yeah, let's solve this using breadth first search because that's what LeetCode wants me to do. And I didn't know how to code it because I don't really code in breadth first search at all. I had to watch a video. I watched LeetCode and actually do it. And so I kind of already know the solution, but I kind of want to reiterate what I've learned, just to kind of melt it in my brain, and maybe for people that maybe will be watching this in the future, I don't know, who cares. So yeah, let's just go ahead and go through my problem solving process with this. So just delete all this. And then let me close this actually. So, given the root of a binary tree, imagine yourself standing on the right side of it. Return the values of the nodes you can see, ordered from top to bottom. Okay, so for input, I know that we're given a BT root of BT. And for output, it just says to return the values of the nodes you can see ordered from top to bottom. So I'm gonna guess it's just like a int, list of ints. And then to note, output needs to be as if standing from right side of input. Basically, collection list of no.vals only most right. Yeah, that makes sense to me. So I'm just gonna go with that. And so we know the input and output. We take some notes. Let's ask some questions. I don't think the question of like what's min no.val is a good question here because it doesn't really matter. I'm gonna skip that, but I guess the good question is what's the min size of input binary tree? And if we can scroll down, it's 0. So we do got to account for like a null root. We should just return null as well. So we know the input and output, got some notes, questions. Let's go through some examples. So basically here, let's just ignore what I wrote down here. Just ignore that. So basically here, what we would return from the right side, well, from the root, the most right is 1 because that's only 1. So we get 1. And then from this level, we get 2 and 3. But the most right is 3, so we get 3. And from this level, we get 4 and 5. So we put 5 because it's the most right. And then even though on this level, there's only a 6 and it's on the left side, it's the most right because it's the only node there, so it's 6. Yeah, those are some interesting cases that we gotta do. Just keep it in count. It doesn't really matter if you go left or right. It just matters what's the most right? So that's one example. I'm sure that's pretty much it. Just to go ahead and match. We do kind of understand the problem, so we can kind of figure out what to use. Well, in my case, originally what I did was I did that first search, and I kind of took in like the node and the depth. So, and we had like a global list basically. And what that list helps us do is that, oh yeah, we also did, I think we did post order search. I'm pretty sure. I'm pretty sure I did post order search, which is like right, left, and then current. That's what I did. Did the right first, and then yeah, and then we would check like if the depth, basically in this case, right? This is the depth. We went right. There's nothing there, so we don't do anything. But we went left. But now we go left, and now there's something there, and so that's why we put it in there, because there's nothing there initially for that level. So you just put it in the result list because there's nothing in the result list at that depth. So that's kind of what I did initially. That was the depth first search answer. But we can also do breadth first search. We're taking a Q or deck in Python. And then we just compare levels. And we kind of do post order, I guess, also. But not really. No, we'd have to do in order because it's a list. I mean, it's a queue, right? So in order. In order, technically, because queue. Queue is first in, first out, so we gotta do that. If we do it in order, then we know that the 2 is yeah, then we know that the 2 is first. And then in here, you would see that we have this one gets this 2 and this 3, right, in a list, right, in a queue. So we remove the 1, then we get the 2. We remove the 2, then we find the 3 is the last one. And then that's how we know that we are supposed to input it in the resulting list. It is if it's the last one in the queue. So yeah, yeah, that's how I kind of understood this problem when it was when I was watching the video for it on how to solve it. So yeah, we can just code that up, but let's do some pseudocode before that, right? So first off, what we want to do is we want to put the result list. So I guess initialize result, res list, and q. So I can say like res equal to empty, and then q is equal to collections is equal to deck, basically, from collections. And then start off the queue, because I know in a queue we're supposed to, or like breadth first search was supposed to be like initialize or do BFS. Or to do BFS, we need to do like while queue is not empty. While queue is not empty, we do this. Right, so we have to initialize the queue with something, so I guess we put it in root, right? I need some water, my throat's getting really dry. Alright, so I was at the point where I said we need to put in the root to initialize our queue. So yeah, so when we did that first search initially, we this is gonna be our first run. So while queue is not empty, right, what do we want to do? Well, first things first, when we access our, you see how in this operation what I did is I said, all right, so go from our current node. I think that's left and right. That's what I did, right? So we gotta do that too. So okay, left and right. Okay, left and right. Oh yeah, I'm forgetting something also. So we need to access the level. So we just need to access level. We do that by saying cur length, level length is equal to the length of our queue. And then from there we can once we get the length of our level, we can access the level itself. So then we got to iterate through level. So to iterate through the level, we say like for I in range, all the way up to level length. What we're going to do is we're going to get left and right of each. But before we get left and right, we gotta pop. So pop cur, get left and right of cur. And then in this case, we know that the last element in the queue, right? So in this case, it'll be 2 and 3, right? So if we remove the 3, if we remove the 2, we get the 3. The 3 is the last element, right? So we can just kind of keep updating the last element. So keep updating last element. And we can say that to note that last element is most right. Right, so keep updating last element, which is our most right. So most right is equal to her, right? And I think this comes in this situation. This comes here in this situation. So pop cur. So cur is equal to cur, I guess. Level, keep updating last element, and get the left and right of cur. Put left and right of cur into queue. So we'd say pop right? No, is it append right? Or add? I don't know. Or was it just dot append? So q dot append left and right. I always do that. And then we just continue on with the whole thing. But as you can see that from here, there's going to be a case where our children could be null, right? We gotta account for those cases. So I guess it's fine that we do pop our null, but in the case where we don't have a where our current is a child, where our current is a null. So if cur null, if cur not null, then do all this stuff, right? Do all that stuff, and then in the end, once we're out of our for loop, we're going to have our most right to be updated already. But there's also going to be a case where we do our last iteration. So basically, we get this level, right? And like, okay, so go left and right, append left and right, right? There's gonna be a case where most right will be nothing. So I guess we can say if there is a most right, then res out append most right, right? And then out of this whole thing, we can just return res, because by the time the queue is empty, then that means that we went through the whole binary tree. So we can just return our result with all the elements that are on the most right of their level, right? So we can just do that. So what we can do is we can just copy this and go to our LeetCode thingy and just copy and paste as a plan. So plan. Right, this is fine. And you just comment and copy it down step by step. So first thing in our plan was to initialize the result list and the queue. So res, we're going to go to an empty list, and then we're going to say that a queue is equal to collections.deck. I spelled deck. Is it like this? Yeah, and then we're going to initialize our queue with the first value with our root node of our binary tree. Then we got to do DFS, right? So do BFS. So while queue is not empty, we're going to access the level. Yeah, and we're also gonna have a most right. So most right is equal to none, and then we're gonna say that the level length is gonna equal to the length of our queue right now. And then we're going to iterate through our levels. So iterate through level /queue. So to do that, we have to say for I in range all the way up to the level length that we're given. We're going to say that the node that we're going to access is just the node the most left. Yeah, so the front of the queue. So I guess say node is equal to the front of the queue, which is basically queue dot pop left. I think that's the correct thing. Let me say, so if it's not null, then we have to update the most right. So most right is equal to node right, and then we have to get the left and the right into the queue now. So that left, and then that append that right. Right, we have to do it from left to right because the right should be the last element in the queue of the level, and the last element in that level is the node that we can see from the right side view, right? And so once we're out this for loop, we're going to have the most right. So get most right of the level. So if most right does exist, it's not null, then we're going to append most right dot val, and then this should keep on running either way. And so what we can do now is that once we're out this while loop, once the queue's empty, we can just return res, which is our output that we're supposed to get, right? Which is just which is all the node vals that you can see from the right side view. So I think we're good. We can just run this and oopsie. Cool, it runs with the 3 test cases that were initially given. Let's go submit and see if it runs with all. And it does. So yeah, that was depth first search solution. I'm pretty sure I have a depth first search solution on this channel with the same name of this video. So yeah, as you can see that I did my depth first search here. Yeah, I did my depth first search here. Let's code. And I believe it's more simpler, but I just did it in LeetCode's way because they want me to do in depth first search, as you can see, breadth first search, as you can see here. So I studied that a little bit. So yeah. So to review its complexities, for time it's O of n because we go through each node once. And for space, it is O of n because we also use a queue to kind of solve this problem, right? And the queue contains basically every node that we're going to feed into it from the binary tree as our input. Yeah,